All right. Can you tell that I'm trying to get these done before Armageddon? I'm getting these done. This is the last piece, the third part of binomial expansion, but the binomial theorem. Ultimately, we're trying to just say, like, pick out a term and describe the term in a binomial expansion. Maybe not the whole thing, but just one piece of it. Why? Because it's fun. Let's try a little warm-up just to get it going. Give me an expansion of that. Pause me until you got it. All right, so your expansion should look like that. Your 2x starts at the fourth power and then drops by 1 each time, etc., etc., etc. And then your b starts at 0 and then increases by 1 each time, etc., 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 up to the point where this is to the fourth and there's no more x. And then the pieces in front, the coefficients in front, are dictated by Pascal's triangle. One way to find them is build the triangle, and you end up with one. This is I think it's 1, 4, 6, 4, 1. So 1, 4, 6, 4, 1. Omitting that middle piece. I'm going to pretend this isn't here. Another way to do it, plus signs between them. Another way to do it is to choose this one. Would be we would go 4, choose 1 in your calculator. So this is n, choose r. So this would be 4, choose 1 in your calculator. This is the correct notation for it, but this is how you throw it in your calculator, and it'll spit out 4, and you can put it in there. Yeah, and then you simplify it to these pieces. So like this whole thing turns into that. This whole thing turns into that. Yeah. Okay. So we're trying to expand these. Expand doesn't mean make the a plus b farther apart. Very funny, Peter. Not me. But we want to show this pattern sort of in a nicer way, in an easier way. Maybe not be able to expand the whole thing, but just find like maybe what the second term is. That's our goal. Let's just jump in. Ooh. So let's just try this guy. We want to write down the first 3 terms and the last 2 terms of that expansion. You know the first 3 terms are going to involve 2x starting at the maximum value, 12, and then decreasing, right, 11. And the last 2 terms, the 2x is going to have no, is going to have 1, well, I guess that's the 3, that's the 3. And here's the last 2 terms. It's going to have 1 in this penultimate unit and penultimate term, and none here in this last term. You also know this 1 over x, you could also call it to the negative 1, is going to start at 0 and then go 1, 2, all the way up to 11 and 12. And then the parts in front are going to be 1, they always are, and then whatever 12th row down, second one in. We say that by saying 12, choose 1. Right? In your calculator, you'd say 12, C1. If this is a non-calculator, you can leave it like that, right? Leave it like that. You don't need to calculate it all the time. You just say, I know how I would find it if I had a calculator. And so this is 1, 12, choose 1, 12, choose 2. On the other side, it's 12, choose 11, which will be the same thing as this one. You don't need to write it down, right? Because they're symmetrical. Like 1, 4, 6, 4, 1 is symmetrical. So the second one in and the second to the last are going to be the same. So here's the second one in, the second to the last. I bet if you throw it in your calculator, you'll get the same thing, and the last one's 1 also. Okay, so let's rip off the Band-Aid and try one of these for real. This is just a standard sort of binomial theorem question. We want to find the 7th term in this expansion. So if we expanded this, we would write this out 14 times and like do all the distribution, and then clean it all up, and then find the 7th one in and write that down, right? Horrible. So we want to do something somewhat easier, right? That's not hard, it's just long, tedious. So let's do something more acute, but intriguing. I know that whatever each term is going to look like is going to have a 3x in it. And the first one in the lineup is going to start with 14, and then it's going to drop by 1 each time. So I'm going to get a 3x to the 14. I'll tell you about that r in a second. And then I'm going to get a 3x to the 13. And then I'm going to get a 3x to the 12, blah, 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 right? What we're doing is starting with 14 and then decreasing by r each time. So in this first term, t1, r is 0. I'm not decreasing that at all. Here in t2, the second thing you see, r is 1. Here, t3, r is 2, because I've decreased this 14, I've decreased it by 1, now I've decreased it by 2, so that's what this r is. Yeah. In this next piece, I'm going to put it in parentheses, negative 4 over x squared. There's a negative in there, I assure you. I assure myself, because you're not here. I'm here without you, baby. And that one starts at 0 and increases as this one goes down by 1. The negative 4 over x squared goes up by 1. It starts at 0, and then it goes to 1, and then it goes to 2, right, the exponent. This had a minus 1, and this had a minus 2, so this change is the same number. Yeah? So this was going to be to the r. Okay. And then also there's this weird mediator in front, that's the binomial coefficient, that's going to be 14 choose r. We saw that in our calculator as 14 choose r before n choose r, right? Now the thing is, like, at first sight I don't know what the r is, but I do know that my term, I'm looking for the 7th thing in, the 7th term. So here term 1 r was 0, term 2 r is 1, term 3 r is 2. R is kind of like the change. So in term 7, this is always 1 less than the term number. The r is 1 less than the term number. So r has got to be 6. So I'm going to put 6 into all of these. Like, this is what any generic term is going to look like based on r, if I knew r. They told me one specific spot that I'm looking for. So I can put in r. So this is going to be 14 choose 6, because the 7th thing I see has an r value of 6. There's been 6 changes in the 14 or in the 0 exponent to get up to there. This 3x is going to start at 14, and then to get to the 7th term, it's going to change 6 times. So minus 6. And then this negative 4 is going to start at 0 and go up 6 times. So it's going to be to the 6th. So I'm going to skip the colors now. This is going to be 14 choose 6. This is going to be 3x to the 8. And this is going to be all this mess to the 6th. Cool. I think that's what they have. Get my scribble out of here. Yeah. Right. So that's where that comes from. Yes, you can clean it up. You can simplify it. It would look like this. You'd put this in your calculator. It would give you this, making stuff up. You'd say I have 8 3's and 8 x's. So you'd go 3 to the 8. You'd put that in your calculator. You'd have that as well. You'd have 6 negative 4's. You'd put that in your calculator, and you'd have 6 negative 2's. Yeah? You'd put this and this and this. They're all just numbers, so you'd multiply them together. You get making stuff up, right? And then you'd put the x's together, and you'd get x to the negative 5. And that is your whole term. I think they kind of cheapskaped you out there, but I think that's kind of the simplified version. I obviously made this part up, but not that part. Cool? Okay, so we're going to try it again. We're going to try to write down, oh, it says without simplifying. Maybe pause me, try that. Here's the answer you're trying to shoot for. Oh, can you see it? Oh, can you see it? Oh, can you see it? And I'll walk you through it in a second. Go. Okay, so the sixth term is the sixth thing I see. So there's been 5 changes in the n value. So 2 to the x starts at 15 and drops a certain number of times r. And then the 5 starts at 0 and increases a certain number of times r. And then we also have a coefficient in front that's n choose r. It's 15 choose the r value. So this is what any generic term looks like, right? This is the t. Ooh. I'm not answering it. They can't find me. This is the rth term, right? This is a generic equation for the term at any r value. I want the sixth term, so I want, that part's not right. This is the generic equation for any term you want based on the r value. I want the sixth thing you see in line. It has an r value of 5, so this should be 15 choose 5. In your calculator, you can put 15 choose 5 with the c in probability. This will be 2x to the 15 minus 5 is going to be 10, and that's going to be 5 to the 5, right? They said don't simplify, so that's sitting there, but if you did, you'd multiply that you'd put that in your calculator. You'd have 2 to the 10th and x to the 10th and 5 to the 5th, and you'd multiply this and this and this together, making stuff up, and then you'd have x to the 10th at the end, and that's the full simplified term number. Cool. All right. So get rid of all this stuff. I think just seeing them a couple of times makes them not so scary. So make it stop. Let's try this one again. So this is x squared plus blah 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 to the 12th. Find the coefficient, like the number in front of x to the 6th. So if you expanded this would be like 2 blah 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 231x to the 4th plus 532x to the 5th plus 421x to the 6th plus blah blah blah. Coefficient says just find me this part, please. Okay, so we got to figure out this term just like we did here, and then we simplify and we steal just the stuff in front of the x to the 10th. The only problem is here they told me they asked me for the 6th term, which wasn't x to the 6th, it was x to the 10th. So we got to do something to figure out the r value when that'll give us x to the 10th. Okay, shake it out, breathe through it. All right, here we go. So, oh, don't look, it'll spoil the fun. No, still spoiling the fun. All right, this is going to start with x squared, and it's going to start at 12 and then drop a couple of, drop 1 every time we go over. This x, 4 over x, is going to start at 0 and increase as you go along in the line, and we're going to have some weird number in front, 12 choose r. That's what every term is going to look like. Now, I'm interested in the term where x has a power of 6 on it. There's some x's here and some x's here. I can't just make the r value 6. It's not going to work because it would work, well, if you put 6 in for r, you'd get a 6 here, but then you'd multiply by 2 and you'd get 12, you get x to the 12th, and it's going to mess things up. So what I'm going to try to do is break this apart without doing any algebra and simplification and put all the x's together. So I'm going to turn it into black and just go 12 choose r. That's going to be a regular number, no x's in it. This is going to be x to the 24 minus 2r if you distributed that in, right? Because if you go x squared cubed, you multiply those. So we're going to do the same thing. 2 times that mess, distribute, distribute, there it is. I'm going to break this up a little bit so this says 4 to the r. Again, that's just going to be a number. I've got to have a bunch of 4's multiplied together. I don't know how many at this point. And x to the negative r. It's in the denominator, so it becomes negative. So I got x's here and here. So I'm going to put those all together, and put my coefficients together. 12, choose r. Still don't know what r is. Still don't care at this moment. There's 4 times r. That's where all my regular numbers are, and all my x's are here and here. And if you add numbers together, add powers together, multiplied by x cubed, you would add these, right? You get x to the 5th, 2x's and 3x's, 5x's. So we're going to do the same thing here and say add these exponents and those exponents. So we're going to go 24 minus 2r minus 1 more r. And so the x's are going to have this exponent of 24 minus 3 r's. Cool? Maybe. We want this exponent to be, let me remember, a 6. We want the x to have a 6 on it. We combined all the x's, so this is the only spot that x's showed up in our simplified term. So we want 24 minus 3r. I want that exponent to be 6. Look, I want that thing to be 6 right there. So set it equal to 6 and solve. You go minus 24 is 18, negative 18, and then divide by negative 3 and you get 6. Oh. That's lame. R is 6 by casualidad, by chance. Oh, that's annoying. The exponent here is 6 and the r value is 6. That's completely coincidence, and that actually is very irksome to me. Anyway, okay, so let's go with it. We know that the r value has to be 6. We're interested in the coefficient, not the whole term, so I don't care about this anymore. This is where all the numbers in front of x are, so put your r value in there. This is going to be 12, choose 6, throw it in your calculator, and this is going to be 4 to the 6. Throw it in your calculator, mash them, multiply them together, and you get that. Making stuff up, right? But you definitely get that. Let's check it and make sure. Always an important step. D-d-d-d-d-d. Nope, nope, nope. 12, choose 6, 4 to the 6th. Was that even close? No, I wasn't close. That's okay. All right, we're going to also do part B, which is, they like this. Find the constant term. Constant term is like 7. Like 7x squared is not constant because x can change, and like 7x to the 5th can change. The value can change because the x can change. But the number that has no x's on it is called the constant term. And so really it has an x on it, but the x is 0. So you play this entire same game, but instead of setting the exponent to 6, you set it to 0, and you solve again for r. In this case, you get r is 8, and you just drop the 8 into here. So the only thing I would change is this. I'd say 12, choose 8, and 4 to the 8, and you get a different big old number. And you know when that big old number occurs, it's because the r value is 8, and it's because when the r value is 8, the exponent on the x is 0. So you have x to the 0. So you have no x's because that's 1, so you just have those numbers. It's called the constant term. Right? All right. One more? Or are you about to pass out? Doesn't matter. We're going for it. So find the coefficient in front of x to the 10th of this. Man, okay. So I know that 3 is going to start at full 10 power and then decrease as we go. I know that 2x x squared is going to start at 0 and increase every time you go over, and I know we got this jive coefficient in front. That's 10, choose r. I don't know what r is. I don't know which term. If they tell me the term, you can go one less than the term and get r, but I don't know necessarily what the r value is here. So what I'm going to have to do is boil all the x values down, set them equal to 10, and then find the r value. Okay, so this seems weird, but that's all right. I guess all the x's are together here, so the coefficient is going to be 10 choose r, 3 times 3 to the 10 minus r. You get 2 to the r from this, and you get x to the 2r, right? This is the only spot where my x's are. I probably should have done this problem first. This is the only rather than the last one. This is the only spot where the x's show up, and I want the exponent on the x to be 10. So I want 2r to be 10. So what should the r value be? 5, right? And so they're looking for just the coefficient. Coefficient is the stuff that's not x. So put 5 into all the r values. So you get 10 to the 5, 3 to the 10 minus 5 is 5, and 2 to the 5. And that's where they get that from. Hoi yoy yoy. All right. Last one, and then I'll have you try to work one on your own. So the only way they add intrigue to this is to make it more complex. And so they're trying to do the same thing, find the coefficient in front of the x to the 5th of this. And the thing is that this is an expansion, and this is not part of the expansion. So we make him go play by himself for a second, right? This would be like x plus 3. This would be x plus 3, and you'd have all of these things going on. You'd have, in this expansion, you'd have 2x to the 6th, and then 2x to the 5th, and then 2x to the 4th. Sorry, I should be putting these in brackets like this. Regardless of what's happening with the other things, when you distribute the 3 in, you get a 2x to the 6th and a 2x to the 5th. The 3 doesn't affect the exponent, right? But then later, so you get 3 times 2x, 3, right? You get 3 times 2x to the 6th. And the 3 doesn't change the 6. But later, when you distribute the x in, this becomes 2x to the 7th. And this one becomes 2x to the 6th. So when you expand this, if we're looking for, don't look. If you're looking for x to the 5ths, if you're hunting x to the 5ths, when you expand this, you're going to get some x to the 5ths somewhere in the lineup. And when you distribute the 3 into that, it won't change those original x to the 5ths. Later, in the sequence here, or maybe I guess earlier, you'll have some x to the, no, it's later. Later, you'll have some x to the 4ths. And when you distribute this x in, it's going to change those x to the 4ths into x to the 5ths. And so you have 2 sets of these coming together. So we're going to try to make the math do this for us so we don't have to think about it as much. So I'm going to ignore this piece and just expand this and look for x to the 5ths for this, and also look for x to the 4ths for that. I know. Who does this for fun? Who studies this and physics in university for fun? All right, so I know that these 2 x's start at 6. I'm looking at just the terms. Start at 6 and then decrease by r. I know that the -1, oh thank you for being easy, starts at 0 and goes to up by 1 each time, and I know that the n value starts at 6 and then decreases, and choose r. I'm ignoring the x plus 3 for a second, just expanding this. So this is what each term is going to look like. I'm interested first in the x to the original x to the 5ths. So this is the only spot that has x's. So it looks like all my x's, I don't have to like cluster them. It looks like my x's have this, and I want that exponent to be 5. This is an r. I want that exponent to be 5, right? So r has to be add an r, subtract r has to be 1, right? So r has to be 1, right? Yeah, okay, easy. Easy. So r has to be 1. So when you get x to the fifths, you have an r value of 1. And that's where I'm going to get some x to the fifths when this 3 distributes into each one of these terms. Where it hits an x, where it multiplies with an x to the fifth, I'll get an extra 3 there, but it's not going to change that. Cool? But I'm also going to distribute this x in, and so I'm interested in x to the fourths as well, because I'm going to distribute an extra x in, and I'll get these x to the fourths becoming x to the fifths, and then later you'll simplify them and put the x to the fifths together. So I'm interested in x to the fourth. So now I want this to be a 4, so I think r's got to be 2. So for this, r is 2. So I need to make one set of this where r is 1, and one set of these with r is 2. Right, okay, so just interested in the coefficients, so not the x's themselves. So the coefficient is going to be for the x to the fifth when r is 1. You'll have 6 choose 1. This will be 2 to the 6 minus 1, and negative 1 to the 1. I didn't write the x to the blah 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 in because it just wants the coefficient. We don't care about the x. So that's one. This is one place where I mean, maybe you want to put it in just so you see it, right? X to the 6 minus 1. This is one term where you'll get the x to the fifth. And this is a negative 1, so this is going to be 6 choose 1. There's 6 ways to do that, 2 to the 6. Oi, this is going to be something horrible. So, and this is negative 1 to the 1, so it'll be negative, and this is going to be x to the fifth, right? And then that'll be in the lineup of this when it's expanded. When we distribute the 3 in there, you'll have a gratuitous 3 stuck in there. Also, we get another set of x to the fifth when x in here is originally to the fourth. So we figured out that was when r is 2, so we're going to play the same game, but it'll be 6 choose 2, 2 to the 6 minus 2, so 2 to the 4, and negative 1 to the 2. Yeah. This x doesn't have a coefficient, so it's not going to multiply in like that, but when it does multiply in, it'll multiply in. This will give us x to the 6 minus 2, which is 4. When this x multiplies in, you get a increase in that exponent. So you'll get 6 choose 2, 2 to the 4, negative 1 squared is nothing, and this is x to the 4th. When you multiply the x in, it becomes x to the x to the fifth. Now they're just talking about the coefficient, so we don't need to talk about the x to the fifths. The coefficient is going to be this plus that. It's like saying if you have 3x squareds plus 5x squareds, you just say I have 3 ducks and 5 ducks. In total you have 8 ducks. Same thing here, I have 2,871 x to the fifths and 342 x to the fifths. Add them together. So I think that's, you add them. Let's see what sort of crazy solution they had for that. 6 choose 2, 2 to the 4th, minus there's the 3, 6 choose 1, 2 to the 5th. It doesn't turn out too gross. Cool. If your eyes aren't bleeding, maybe you want to try one of these on your own. Maybe not. There is some practice. Well, I mean, you have the practice. I'm going to rip through this one with you. This looks like this. When you expand this piece, it expands like this. We're looking for the x to the 5th. Somewhere along the line, we have some x to the 5th. Oh, this is kind of cool because this is x squared. So you need x to the fourths, and I don't think you get any from anywhere else, right? Like when you expand this, you get x squared to the eighth, then seventh, then blah blah blah, third, then second, blah 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 blah. I stopped here in my example because this gives you x to the sixths. Not interested, right? We're interested in x to the fifths. When you multiply the 2 in, it'll make an x to the fifths be the same power, but when you multiply the x to the x in, it'll increase this power by 1. This is x to the sixth, so that's not what we want to work with. But this x to the fourth, when the 2 multiplies in, it'll stay x to the fourth, but when the x multiplies in, this piece will turn into x to the fifth. The strange thing is, or hard to see thing is, I'm not going to get an x to the fifth that naturally shows up in any of these original terms, because you always have x squared being multiplied by something. So this is even, this is even, this is even. All of these are going to be even. You'll never get a natural x to the fifth out. You'll only get an x to the fifth showing up when an extra x drops in, and it's going to be when it links up with this x to the fourth. So we're going to see it in that term. Right? Oh, thanks for writing that out a million years ago. So the 2 doesn't really do anything to get us an x to the fifth. We'll never see an x to the fifth originally, so multiplying by a 2, not going to show up. An x to the fifth is not going to show up anyway. An x to the fifth is going to show up when this occurs. So when x to the fourth occurs. So you need x squared to the 8 minus r, you need 1 to the r, and you need 8 choose r. I'm trying to figure out what the r value is. Looks like this is going to occur when my exponent is, when the exponent is 4. That's going to have, this is the only place where the r values, or where the x values show up. So I need x to the 16 minus 2r. Right? I need this exponent, I want that to be 4. Right? So I want 16 minus 2r to be 4. Once it's 4, I can drop the x in, and I'll get one term that has x to the fifth on it. I know. Hey. Say hi to Mr. Bruce. Mr. Bruce loves binomial theorem.
It's my second favourite theorem, behind Fermat's last theorem.
Yes, see, that's what I'm talking about.
AN plus BN equals...
Alright, so I need this exponent to be 4, trying to make it 4, so when we distribute the x in, we get to 5. So what do we do? Subtract, you get 12, negative, you get negative 12 is negative 2r, you get negative 12, you get r is 6, it's always 6, guess 6 on the exam. And then we can plug these 6's back in for these r's, so you get 8 choose 6. They want the coefficient, and so the coefficient is not the stuff with the x, so we don't care about this. And then this is 1 to the 6, which is 1, so this is just 8 choose 6, which is 28. Neat. Sorta. I think binomial theorem is a favorite of the IB because it's really theoretical. It's really just like hard to think about. It's very abstract, and they like seeing your just straight up brain crunching power. Can you connect all these dots? It's a challenge. Give it a shot. It's not very long. The questions are very predictable. This is like question style number 3 out of 4. There's like 4 different types of questions. So they're very predictable. They kind of look scary, but definitely like this is a very specific, like that's one of the questions on the exam. Absolutely. Every year there's one like that, and like that's pretty much the whole thing is like find the 9th term of this. Sometimes they'll like throw one at you that's like find the common factor, the constant term, and the constant term is when x equals 0. that sort of thing. So this is style number 1 of the questions. This is style number 2 of the questions. This is like a hard one. This is sort of like an easy. Well, this is sort of like an easy one. And then constant term is the same thing, but you need to know that it's x to the 0. That's style number 3. They're always the same, but they're satisfying, I think. Cool. Hope that helps. Sorry about the movement.